in Algebra 2, we're going to go ahead and start the notes for section 3.5 so that you have them. We'll go through the exercises in the video, so make sure you get all of this in your notes, and then we will be practicing when we get back into class tomorrow. So I'm going to go ahead and just start off with the notes rather than the bell ringer, so just go ahead and skip that one for now. But this section is on linear programming. So business professionals use algebraic concepts all the time to desert. One of the ways they do it is to determine reasonable prices so that they minimize costs but maximize profits. Obviously, if things are too expensive, people aren't going to bother to buy them. If they're not, if they don't match the cost of making it, you're never going to make any money. So we have to find the balance between those two. Inherent in these situations are certain limitations or constraints. Those are created by the lines of your inequalities. All right, so we call this linear programming. Use lines and the way they intersect to do it. The technique used to maximize or minimize a particular quantity, represented by the objective function. That's always going to be found at the vertex or the intersection of the lines. Under a given set of inequalities, the constraints. The solution, excuse me, to a system of inequalities formed by the constraints is the feasible region. So the idea is that anything in that region is going to help you in some way maximize or minimize a particular quantity based on what you're looking for. But the vertices, the intersection of the feasible region are the possible answers for your maximum and your minimum. All right, let's continue to get through the written part of the math, and then we'll get to the examples so you can see what I'm talking about. I just wanted to check one of the principles. So it's pretty straightforward. The vertex principle says that if a maximum or minimum value of the objective function in a linear programming problem occurs, if there is an answer, it will occur at one or more of the vertices of the feasible region. So remember, like if you have three lines intersecting, maybe I can get my pen to work here, right? These are the vertices. These are the points. So we look at those points, plug them into the kind of combined system equation to find out which one gives us a largest answer and a smallest answer. That's your maximum and your minimum. All right, let me show you what I'm talking about. Example 1, we've got a couple of different slides on this one. The first one covers the first step, which is you have to graph the constraints. We have to graph our inequalities. Step 1, graph each constraint. This gives us our feasible region or our solution. Each constraint. Okay, so we have x is greater than and or equal to 0, but less than or equal to 4. So I have one, wait, that's not the x. Hold on. There we go. This is x equals 0. There's one side of that constraint. The other one is 4. 1, 2, 3. 1, 2, 3, 4. Here we go. All right, there's the first one. That's my, do that every time. Second one, change to blue. Y is greater than or equal to 0, but less than or equal to 2. So that gives me this one here. Up to the area in between those is its solution. So that's 0. And then the last one, I'm just going to convert it into slope-intercept form by moving that x term. It's going to change colors. I get y less than or equal to negative x. All right, so 5 is my y-intercept. 1, 2, 3, right here. And it's the slope is -1, so I'm going to use -2 over 2 to graph down to right, down to one more time. Down to 2, just the whole thing. That's close. Sure. It's equal to, so it's solid line. All right, so this is our y is less than or equal to negative x plus 5, so it means it's everything underneath that line. Also, it's between the two blue lines and the two red lines, so our feasible region right here. Okay. The second part of this, the second step, is we have to find the coordinates of the vertex. All right, so we've got a few here. We've got this one here, which is the origin. We've got one here, here, and here. So we've got 5 different vertices. So let's go ahead and jot those down. I know I'm going to start at the bottom one here, since that's the origin, and just move, I'll just move clockwise from there. So our vertices, which are in form x, y. The first one obviously is the origin, 0, 0. The one just above it, x is 0, y is now 2. Now I'm going to go right. So I know it's up 2, right 1, 2, 3. So my x is 3. And then I'm going to go down 1. So down 2, y equals 1, but then right to x equals 4. So 4, 1. And then I go down again, where x is 4, and now it's on the y-axis, or x-axis, so 0. So that should be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, so there's our 5 vertices. Now, in this case, we're finding the ordered pairs that will maximize and minimize the objective function z equals 3x plus 5y under the given constraints. We've graphed the constraints. We've found the coordinates of the vertices. So now that third step, we have to use the next slide. And in the next slide, you can see I've gone ahead and given you an image from the book. Looks exactly like ours, as long as I put my numbers in right. 3, 2, 4, 1, 4, 0. Yeah. Okay, so let's go ahead. We have our x and y. We have our ordered pairs. And what we're doing is we're plugging them into z, which z equaled, let's go back here, 3x plus 5y. 3x plus 5y. And then that's going to give us some solution for z. Okay, so my first ordered pair was the origin, 0, 0. So this one, z equals 3 times 0 plus 5 times 0. So that means that z equals 0. All right, the next one was 0, 2, I believe. So z equals, in this case, the x is the 0. So 3 times 0 plus 5 times 2 is 10. So that means z is 10. The next one was 3, 2. All right, so I'm just going to 3 times 3 plus 5 times 2 plus 10. It looks like that, so that means my z for that one is 19. The next point was 4 and 1. It's 3 times 4 plus 5 times 1. 12 plus 5, which is 17. And then our last point, 4, 0, 3 times 4. Okay, so now all you do is you look at those values of z, And you can see here, oops, hold on just a second. Just make sure I got this all straight here. 0, 12, 17. Oh, okay. I see. In the book, they put them so your Z's were in numerical order. All right, so stop it, cat. So in this case, what you're doing is you're looking at which one of these points gives you the minimum solution, the objective function, and which one gives you the maximum. So we can see here at the origin, there's our minimum. Excuse me. That's the lowest value of z that we have. So yeah, you don't have any change in x and y. Makes sense. That's going to be our smallest. But then we can see that this point right here at 3, 2, there's our maximum. So our maximum value, which is 19 at 3, 2. And honestly, I think this will make more sense when we get into the word element. But for now, you can see how mathematically, even if you don't necessarily understand what it is you're finding, you can see how to find the solution. You simply plug in your x and y into the appropriate variable, do the simple math, and it chucks out an answer. Whatever the biggest one is your maximum, whatever the lowest one is, there's your minimum. All right, let's look at somewhat similar, and I've gone ahead and given you the graph on this one. Minimize the objective function f of x and y, the function of the ordered pair, where 5x plus 2y under the given constraints. So in this case, we're wanting to minimize the objective function. So every constraint we have simply keeps it from getting all the way to the origin, keeps it from getting there. So it's everything greater than x equals 0, everything greater than y equals 2. Everything greater than the x and y is greater than or equal to 4, and the 3x plus y is greater than or equal to 6. So you can see here, they didn't show you the x is greater than 0 simply because that's your y-intercept. So that's kind of understood right here along that y-intercept. That is a mess. Okay. And so I went ahead and gave you the graph where they've highlighted. So because the point, oh my gosh, hold on. My cat is just laid down on my notes. Okay. Sorry. Okay, so in this case, the important part is that the feasible region is unbounded. So you can see how it goes forever up and to the right. However, it does still have the 3 vertices. It has the one at the that one y-intercept, 0, 6, 1, 3, and 2, 2. So what we want to do here is plug those ordered pairs into our function and see which one gives us the smallest value, the minimum. Excuse me, minimizing here. So let's go ahead and put those in. I have my ordered pairs, x and y, and I have my function 5x plus 2y. All right, so my first ordered pair of 0, 6, and then 1, 3, and then 2, 2. All right, so I'm going to plug those in. That's 5 times 0, which is just 0, plus 2 times 6, 12. So my solution, call this f of x and y. They didn't use a separate variable like z in the last one. So the solution to the function is 12. And then I put in 1 and 3. I've got 5 times 1 plus 2, 3. This is 5 plus 6. So that gives me 11. So already that one's less than the first one. So I know the first one's out. Now let's plug in the last one and see what we get. 5 times 2 plus 2 times 2 gives me 10 plus 4. So that one's 14. So that's even bigger than the others. So that means that the point that minimizes the function is that 0.13. So the objective function has a minimum value say f of 1, 3 equals 11. There's our minimum value of 11. All right, so I've put the steps that I've used to solve these on the 8th slide. Solving a linear programming problem, you write an objective function for the quantity being maximized or minimized. So you write the inequality, the main function, I guess, the equality. You write a system of inequalities modeling the constraints. Then you do what we've been doing. You graph the feasible region, find the vertices, and then substitute the coordinates of each vertex into the function that you made to determine the maximum or minimum. All right, so let's work through this last example and then we'll be done. So example 3, the company wants to maximize its profits from 2 snowboards, the Snow Pro and the Mountain Flyer. So I've organized the information we have. The company has a budget of $15,000 for labor and $27,000 for materials. The material cost is $50 for each Snow Pro, $90 for each Mountain Flyer. The labor cost is $50 for the Snow Pro, $30 for the Mountain Flyer. So if the profit for each Snow Pro is $25 and for each Mountain Flyer is $60, how many of each snowboard should be made to maximize profits? And then what is that maximum profit? All right, so the first thing we need to do is define the function for profit and the quantity that is to be maximized. So define the function for profit. So first off, I'm going to go ahead and define x is the number of Snow Pro. Oh. Excuse me. Number of Snow Pro boards made, and the y is going to be the number of Mountain Flyers made. All right, so I know that the profit of some combination of x and y is equal to, let's see, what's the profit of the Snow Pro? So 25x plus, they're making a lot more money off those Mountain Flyers, 60y. There's the function of our profit. So that's the one that we want to, that's one of the ones that we're going to want to graph and use. Oh, I have that gigantic slide. Hold on a second. Okay, so now we've got our profit equation. That's like our main equation. You can think about in the first example, that was your z equals something x and y. So now we need to define our constraints. These are inequalities. All right, so first off, we know they can't make negative boards. That's literally impossible. So I'm going to define the number of boards. So the number of Snow Pros needs to be greater than or equal to 0, and the number of Mountain Flyers made needs to be greater than or equal to 0. So this part, let's see, can't that one is. All right, so then they gave us some other constraints. They said that the budget for materials is $27,000. So let's look at materials. The material cost for a Snow Pro is $50, and the material cost for the Mountain Flyer is $90. So this means that 50 times the number of Snow Pros made plus, is it 90? It's expensive to make, material-wise anyway. 90y needs to be less than or equal to, what was the material? $27,000 is the budget for material, right? So they don't want to spend more than $27,000 on materials. Okay, so this is our materials. budget with constraint. Usually money is your constraint. And then we have a labor constraint. So the labor cost is $50 for the Snow Pro, $30 for the Mountain Flyer, and it needs to be less than or equal to $15,000. There's their budget for labor. So I already lost 50x plus 30y needs to be less than or equal to 15 for labor constraint. Cat. Okay, so this gives us our constraints. Just double check. Okay. So we have those, and now we need to graph the constraints. So this is step 3. So we have, let's see, start with red. We have x is greater than or equal to 0, and y is greater than or equal to 0. So that means that we have constraints on our x and y axis. I'll keep those the same color since they already exist as the x and y axis. Then we had, okay, we have the other two. Shade the feasible region. Okay, let's go ahead and graph. Let's see, what am I there? 50x plus 90y. So 50x plus 90y is less than 27,000. I'm just going to find my x and y intercepts. So that means that if x is 0, then I divide this by 90, and my y is less than, I think it's less than or equal to 3. All right, so I've got my y-intercept. The first one, oh, how am I going to see? We'll make this 100, 200, 400. Each dash will be like a 50. Same thing here, 100, 200, 1, 2, 300, 400. Okay. All right, so the y-intercept is at 300. So right here, and the x-intercept would be 50. I would make that 0. So 50 goes into 27. 5 goes into 27 5 times. We have 2 left over. 5 goes into 24 times. 1, 0. Okay, so the x-intercept is at 540. So it's going to be somewhere about right here. Here's that by Merriweather. Stop it. Let's see, what was that? That was materials. I'm just going to call that one nets. Okay, so the other one was 50 and 30 and 15. It would be easy. So 50x plus 30y is less than or equal to 15,000. So if x is 0, that means that y is less than or equal to, that's 3 goes into 500. And then I'll make sure these are like y, that's our And then the x, if that's 0, then it's 300 is the x-intercept. Okay, so y-intercept is 5. Oops. Up here. And 3 is right here. So graph those. This right here. That is my labor constraint. All right, and that point is somewhere in the middle of something. And mine actually doesn't look quite exactly the same as theirs. So we're going, it's obviously the intersection is not this vertex. Now we know this vertex, right? This one right, make them black, just so they're a little more visible in this copy. So we have this vertex here. We have, oh, that's why I put that in the absolute wrong place. Hold on, let me fix myself here. That 3, that's interesting. That 300, it was the green one, should have been on the line right there. Okay, so that's ish. Oh, it's close. There's that one, and then there's this one. I don't know if y'all can hear this cat purring. She refuses to leave my desk and is absolutely thunderstorm. Okay. Either way, we still have the situation where we don't know what this guy is right here. But that's one of our vertices. And then we have this vertices down here. Cat. It's, let's see, x is greater than 0, but it's less than, okay, the labor cost is less than. So the highlighted area is going to be, this is our feasible area here. There's everything down here. So we have to find those constraints. So let's go ahead and do that. But we've got to figure out what that middle one is. Obviously, we know there's one at overseas. Have one at 0, 300. And then we have one down there at 0. We obviously have one at our origin. That's probably not going to give us anything. And then let's look at, we got to calculate that middle one. So I'm going to do that using I'm going to use elimination. Since both of those x's are 50, I'm going to use the 50x plus 90y cat, go away, equal to 27,000. And then make everything negative in the other one, minus 50x minus 30y plus 30 to negative 15,000. That gets rid of my x, and I get 90 minus 30, so 60y less than or equal to 27 minus 15, 12. So when I divide by 60, I get y is less than or equal to, let's see, those cancel, 200. And then I'll plug that 200 in to one of them. Well, let's plug it into the smaller one. Other two. So actually, it really doesn't matter which one we use. I'll use the 50x plus 90 times 200 less than or equal to 27,000. Three zeros. Let's cancel. 5 goes into 9 one time with 4 left over. 5 goes into 40 8 times with no and then 0. All right, so that means that this point right here is, hopefully you could see it, 180, 200. That's such a mess. I'll just put it off to the side. Right there. 180, 200. Which looks, mine looks a little less than 200, but that's probably just because of my graphing ability. Definitely looks pretty close to 180, but it probably just needs to intersect a little bit higher. So it has more to do with me drawing straight lines than anything. And that's also why doing it algebraically is so much more accurate to find your points than trying to graph it exactly right on the graph. So that's the last vertice that I was looking for. So let's go ahead and write those over here. The very, very last step is we need to evaluate the objective function. This is step 4? Evaluate the objective function. In this case, that was our profit function for each vertex, each vertices, to determine the maximum profit. Again, we're looking for maximum profit, and then the, what was that formula? 25x plus 60y. Down, 25x plus 60y. Okay, so let's go ahead and get those vertices. So that's our x and y. Not even going to bother with 0, 0, because that's going to give us our minimum 0. But let's use, let's see, we had 300, 0, we had 0, 300, and then we had 180, oops, 200. Okay, so we're plugging that into 25x plus 60. So I have, in this case, I just have 25 times 300, 60 times 0 is just 0. So that gives me 75, 75, 2 zeros on there. All right, so P of 75. For the next one, the x term is 0, so this is 60 times 300. 6 times 3 is 18, and 3 zeros, that's big. So definitely more than the other. And then for the last one, we have 25 times 180 plus, I'm going to use some word here, 60 times 200. Let's see, so that gives me 25 times, oh, 25 times 10 is 200. And, oh, let's just use the calculator. I'm not going to try to do that. 25 times 18. 4, 5, 0, 0. And then this one, 6 times 2 is 12 with 3 zeros. So 4,500 plus 12,000 gives me 16,500. So that means that the 18,000 is my max profit, and it can be achieved. That's where, let's see, that's this guy down here. So my X is 0, and X was Snow Pro, and 2 was Mount. So this means that the max profit is $18,000, selling no snow crows and 300 mountain flyers. And there is our solution. All right, hope y'all got all of that. Definitely just make sure you have the notes. They're as neat as possible. We will practice this more in class as well as before we take the quiz. And that is all for now. See you guys in class tomorrow.